Hi guys, so let's talk about section 9.3 using general angles and radian measure. Okay, so hopefully last time you remembered to figure out how to convert radians to degrees and degrees to radians fairly quickly using that diagram I gave you. So today we're just going to go and talk about general angles more formally. Okay, so angles that are bigger, that are not acute angles. And how do we do trigonometric ratios of those angles. And so here it says let theta be an angle in standard position, so remember standard position centered at the origin, and let xy be the point where the terminal side of theta, the terminal side being this side right here, okay, where the terminal side intersects the circle x squared plus y squared equals r squared. Notice r squared can be anything, of course. And it's the radius of a circle, so as shown in the diagram. Then the six trigonometric functions of theta are defined as follows. Okay, so sine of theta, no matter where theta is, so at right now theta is this angle, but theta could be here, theta could be an angle in the third quadrant, theta could be an angle in the fourth quadrant as well. Okay, oh no, not there, sorry, going all the way around to here, theta could be an angle in the fourth quadrant as well. Okay, so any case, for any angle theta with a circle with radius r, this is the relationship between sine of theta. Sine theta is y over r. Okay, so if I'm going here, sine of this angle theta is y, which actually is this distance, over r, which is the radius. Okay, but if you look at this carefully, you'll see that still is, if you think about it as a triangle, okay, still kind of like an opposite side and a hypotenuse, but it just doesn't look right because this is the angle, but it looks like I'm looking at the triangle from this perspective. Now, we'll get to that a little bit later, why that works, how that works, okay? And those are called reference angles. We'll talk about that in a little bit. But for now, just suffice it to say that, this is the definition. So the sine of theta is y over r, and then the cosine of theta would be x, which would be kind of like the adjacent side here, over the radius. Okay, the length of this side, which is x, over the radius, and the tangent would be y over x. Okay, so that lets me, and then you know that cosecant, secant, and cotangent are the reciprocals, right? And then of course the radius, because it's a radius of a circle, r, or kind of like the hypotenuse in a triangle that we've been talking about, the radius is always positive. Okay, we don't write r as a negative number ever, but x and y can be negative depending on where they are in the coordinate plane. Okay, but radius r is always positive. Okay, and so yeah, and these functions are sometimes called circular functions. Okay, so basically all we're doing is saying what happens when I take sine, cosine, tangent outside of the first quadrant. This is where all of our little triangles we've been memorizing lived. What if I take them outside of the first quadrant? How do I deal with finding trigonometric ratios then? Okay, for bigger angles than 90 degrees. And so that's it. Just the definition. You can just use the definition and solve problems. Okay, and so what you're doing is this. It says evaluate trigonometric functions given a point. I would suggest you draw a picture. If you don't want to draw a picture, that's also fine. If you just want to totally memorize this stuff, that's okay as well, I guess. But you can just draw a picture to help you do this very quickly. And then you say, draw the point. So -4, 3 would be here. Okay, and so this is the terminal side. of my angle, and this is the initial side of my angle. Okay, and so this angle would be theta, kind of like the diagram. Okay, and it says evaluate the 6 trigonometric functions of theta. All right. Now the problem you have is I know that my x comma y here is -4 comma 3, but I don't know how long the radius is. How long is the radius? Okay, to that point. So, and again, what you're thinking is there's a circle here, and that's the radius. Okay, so the question is, how long is the radius? And you say, oh, the radius, I can drop an altitude here and think of Pythagorean theorem. So I can say the radius is -4 squared plus 3 squared. So the radius squared is, what's that, 16 plus 9, so the radius squared is 25. So the radius is 5. Okay, so now I know that the radius here is 5. And that's, notice if you look up here, all you need is x, y, and r, and then you can do any of these trigonometric functions. Okay, and so let's do, they said do all 6. So sine of theta, again, I don't know what theta is. Theta is the angle that puts me there. Later on, you'll see that we can actually figure out what angle theta is. They said it's y over r. So in this case, the y coordinate is 3 and r is 5. Okay, so it's just 3 over 5. Again, x, y. And we have it in our picture there too, x, y. Okay, and then cosine theta is x over r. Okay, x over r. And so that is just -4 over 5. Okay, so the x coordinate is -4. Now, please don't. If you're thinking triangles, you're thinking, wait, a distance or the length of a side of a triangle can't be negative, which is correct. But what we're doing is saying where in space in the coordinate plane am I? Okay, so the negative is important for telling us the position of the angle, actually. All right, so don't think about necessarily the distance exclusively. The distance or the length of the triangle, or the terminal sides, components, or something like that, is 4, but the negative tells me where I am in space. All right, and then tangent theta, they said, is y over x, so that would just be 3 over -4. Okay, and then the other 3 I'm not going to do. You can go do those. That's just cosecant and all that other stuff. So you, as long as you remember, please, that cosecant is the corresponding angle here. Secant is the corresponding, well, not angle, trigonometric function, and cotangent is the corresponding trigonometric function here, and they're all just reciprocals. So this one would be 5 over 3, and so on. Okay, so you can take reciprocals. I don't really think I need to show you all that. All right, and then example 2 is letter B is pretty much the same thing. Okay, pretty much the same thing. I'll do this a little bit quicker here. All you're doing is drawing the point. Remember, this is x, this is y. So you draw your point, -9, let's say -40 is out here, -9 is here. All right, so that would make this my radius right here up to this point. Okay, and this is my x, and this is my y, or you can do it like this: -9, -40, this is my x, this is my y, and then you just have to figure out the radius. And I mean, this is just Pythagorean theorem. If you do that, you find out that the radius is 41. Okay, so you're just using the idea of making an altitude here and using Pythagorean theorem. You get the radius is 41. And then you just do the 6 trigonometric ratios. Sine of theta is, again, y, which is this, over the radius. So y is -40 over 41. Then the cosine of theta is x over r, which is negative 9 over 41, and then the tangent of theta is just x over r. Sorry, y over x, which is negative 40 over negative 9, which would be 40 over 9. Okay? And then you can go do all the other ones. Just remember again, cosecant, secant, cotangent. So cotangent of theta here would just be 9 over 40 because it's reciprocal. And you can do the rest. Okay, just a simple definition. I think once when we do reference angles in a little bit, maybe this will make more sense where the definition comes from and how it works. Okay, so I'll show you that in a second. So then we talk about the unit circle, and this, I have to be honest with you, a lot of students really get confused by this. I think if you stick with this understanding of the definition of the trigonometric functions for general angles that are bigger than 90 degrees, I think you'll be okay. All right, so the unit circle says consider a circle that has radius 1, basically, which has center 0, 0, okay, like this circle right here. All right, and then it says we call that the unit circle. Unit because radius 1 is 1 unit. Okay, so they call it the unit circle. And then the values of sine theta and cosine theta are simply the y-coordinate and x-coordinate, respectively, of the point where the terminal side of theta intersects the unit circle. Okay, so that seems a little bit confusing, but if you think about this, if we said earlier sine of theta is y over r, okay, and the radius is always 1 on the unit circle, okay, then anywhere on the unit circle, the sine of theta is actually just equals to the y-coordinate. And anywhere on the unit circle, the cosine of theta is actually only equal to the x-coordinate. Okay? So, why are we talking about this? The main reason is for us to figure out quadrantal angles. Okay? And you'll see why in a second. We have a nice definition here for general angles right here, and we can draw a triangle and find a radius and all that kind of stuff. But the question is, what happens when I'm at this angle right here, which is 90 degrees, or when I'm at 180 or 270 or 360? What happens at those angles? That's the question. So those are called quadrantal angles. Okay, so it's convenient to use the unit circle to find trigonometric functions of quadrantal angles. So what are quadrantal angles? An angle in standard position whose terminal side lies on an axis. Alright, so that's a little bit abstract. I think you can draw this. Okay, here are my axes. Alright, this is what they mean when they say that. And so what are the quadrantal angles? Well, 0 degrees is a quadrantal angle. Okay, and then 90 degrees is a quadrantal angle. So 90 degrees would be initial side here, terminal side there. Okay, so they said the terminal side lies on an axis. So 90 degrees is this angle, and its terminal side lies on this axis right here. Okay, so that's why it's called a quadrantal angle. And then if I make a bigger angle, which we call 180, okay, so the terminal side of 180 is here, so it lies on an axis, and so that's 180 degrees. Okay, so 180 is also a quadrantal angle. Well then, if I go all the way here, this terminal side is on an axis, so that's 270 degrees, so 270 degrees is also a quadrantal angle. And then if I go all the way around, I get to there, then I get 360 degrees, and that's also a quadrantal angle. Okay, so those are my 4 or 5 actually quadrantal angles, 5 quadrantal angles. Of course, there are infinitely many. You can keep going around the coordinate plane and you know that there are infinitely many coterminal angles, but those are the basic 5 quadrantal angles. So the question is then, how do I find sine of 90 or sine of 180 or cosine of 180 and those kind of things? Okay, so um, basically you just consider the unit circle and say, what are the coordinates on the unit circle? Basically is what you're doing. Okay, this is the easiest way to do this. And so what you're saying is, if sine of theta is just y, cosine of theta is just x, then you can easily evaluate this if you just say radius is always positive and it's always 1, and then this coordinate here would be 1, 0, so x, y. This coordinate here, which are where the quadrantal angles are, this coordinate here would be 0 and 1, so x and y, and this coordinate here would be negative 1 and 0, and this coordinate here would be 0, negative 1 for x and y. Okay, and that's basically all you need to figure out all the quadrantal angles. Okay, and so you say, use your understanding of the unit circle to evaluate the 6 trigonometric functions for all 5 quadrantal angles. Okay, so that's actually a lot of work. You have to go 6 trigonometric functions for each quadrantal angle. I'm not going to do all of that. That's a lot of writing out. Basically, if you understand this, then you don't have to really memorize all this stuff. You can just, if you know this, then from here you can easily come up with your trigonometric functions. So let's pick one. So let's again say this is 0 degrees, 90 degrees, 180 degrees, 270, and 360. Okay, so how about we do maybe 2 of these, and let's see how that goes. So let's say we do 90 degrees. Okay, so let's say, what is sine of 90 degrees, if that's my angle. All right, and so this says sine of the angle is just equals to y. All right, so it's really y over r, which is our previous understanding based on our definition, but it's 1 over the radius, which is 1. Okay, so that would mean 1. All right, and then cosine of 90 degrees, cosine of 90 degrees would be x over r, but x is 0 at 90 degrees. If you look at this coordinate here, x is 0 over 1, which is 0. Okay, and then tangent of 90 degrees. Now what do we say for tangent? Tangent is y over x. Okay, tangent is y over x, which would be, in this case, 1 over 0. Okay, so that would be undefined. All right, so tangent of 90 is undefined. And then you can continue and do cosecant of 90 degrees, which is just the reciprocal. That's the same. And then secant of 90 degrees, which is the reciprocal, which is undefined. Okay, and then cotangent of 90 degrees is the reciprocal, which is 0. All right, so that's how you deal with, let's say, 90 degrees. So pick another one. Okay, I don't know, let's say we do 180 then. All right, let's consider the quadrantal angle 180 and say sine of 180 is, well, sine is just y. So you can keep writing y over r, but you don't really need to do that. Okay, the sine of 180 is just y. Okay, just the y coordinate. So the y coordinate is 0. All right, and then cosine of 180 is the x coordinate. The x coordinate, negative 1. Okay, and then tangent of 180 is y over x. Okay, so y over x, 0 over -1, that's just 0. Okay, and so on. So cosecant of 180 is the reciprocal. All right, so if it's 0 over, let's see here, sine is y over r, is r over y, so that's 1 over 0, so that's undefined. Okay, and then secant of 180 is reciprocal, and the reciprocal would be r over x. In that case, there would be 1 over -1, which is -1. Okay, and then cotangent of 180 would be the reciprocal of this, which would be undefined. All right, and so you can figure them all out this way. So it's not really something you definitely don't want to memorize all this stuff. Just remember this, and then you'll be fine. Okay? And please, of course, quadrantal angles, 0 degrees is 0 radians. Okay? 90 degrees is pi over 2 radians. 180 degrees is pi radians. 270 degrees is 3 pi over 2 radians. And 360 degrees is 2 pi radians. You should be able to work very easily in either degrees or radians. Okay, they're the same. All right. So let's talk about reference angles. This is very, very important for you. Okay, reference angles allow us to quickly evaluate these when the radius is not of the circle that you're working in is not simply 1 or some easy number. Okay, and there's again, you'll see reference angles are angles that we use to evaluate trigonometric functions of the most common angles that we use. So the most common angles that we use, again, you remember these two triangles, 30, 60, 90, and 45, 45, 90. And you remember this stuff. Yeah, my triangle doesn't look right, but okay. I drew the angles in the incorrect position, but this is what it would be, okay? So those are our most commonly used angles. So what if I take this triangle and I have it in this quadrant? Or if I have it in this quadrant or this quadrant, how do I quickly figure out the answer then? Okay? And what are the corresponding angles? This is the reason why you memorize that picture with all the different angles in degrees and radians and all that kind of stuff, the diagram from our previous lesson. Okay, that's why I memorized that thing, because those are the angles we use very, very often outside of the first quadrant, and so we can quickly figure out the trigonometric functions of those angles by using reference angles. Okay, so it says let theta be an angle in standard position. Of course, all our angles are in standard position. The reference angles for theta is the acute angle, theta prime. So this is important, please. We call a reference angle theta prime, formed by the terminal side theta of the x-axis. So please, x-axis. Reference angles are formed by terminal side and the x-axis. Okay? And the x-axis. So, if you look at this carefully, here's a reference angle. It's the angle from the x-axis to the terminal side. Here's a reference angle. It's the angle from the x-axis to the terminal side. Here's a reference angle. It's an angle from the x-axis to the terminal side. And inside the first quadrant, we don't need reference angles because we have triangles to give us all those ratios. Okay, so please remember, a reference angle is always formed by going from the x-axis to the terminal side. X-axis to the terminal side, x-axis to the terminal side. A reference angle never lives here. There's no theta prime here. There's no theta prime here. Okay, and there's no theta prime here. Those are not reference angles. Reference angles are formed by going from the x-axis to the terminal side of the angle. All right, please remember that, because many students get that confused and they keep drawing reference angles in the wrong places. So these are not reference angles. These are not reference angles, and these are not reference angles. Don't do that. It's always going from the x-axis to the terminal side. I'm saying this 300 times, but it's very, very important because a lot of students mess that up. Okay. The relationship between theta and theta prime is shown below for non-quadrantal angles, such that theta is between 90 and 360. Okay, so all the angles that are bigger than 90 degrees and less than 360. All right. So let me show you how to do this. It says find the reference angle for theta prime for the given angle theta. Okay, so I'm going to show you the easiest way to do this is draw a little picture for yourself. But this relies on your understanding of radians and degrees. So where is 5 pi over 3? That's the real question. Okay, so what I showed you last class was, or in the last video, was the way you think about how to position this in space is 5 pi over 3 is almost 6 pi over 3, which is 2 pi. Okay, now this is happening in your head. You don't have to write this down. This is a mental process, all right? So 5 pi over 3 is almost 6 pi over 3, which is 2 pi. So almost 6 pi over 3 means I'm almost at 2 pi, which is here, but I am pi over 3 less than 2 pi. Okay, so here's my angle. This angle is 5 pi over 3, and if I go another pi over 3, I'd be at 2 pi. Okay, so notice what we just did. We drew an angle from the x-axis to the terminal side of my angle. Okay, and that would mean that the reference angle here would be pi over 3. All right, now please, this is saying find the reference angle theta prime for the given angle theta. So if the angle is given in degrees, use degrees. If the angle is given in radians, use radians. Okay, so my reference angle for this theta prime would be pi over 3. All right, next one, negative 130 degrees. So remember, negative, you go clockwise starting here. So this would be negative 90. And then negative 130 would be somewhere here. Remember, this would be negative 180, so I'm not there. Okay, so this angle would be negative 130. And then the question is, the reference angle is formed from going from the x-axis to the terminal side. So how far am I away from 180? Okay, or from negative 180? In this case, this would be 50 degrees. Okay, so theta prime here would be 50 degrees. So theta prime is 50 degrees. All right. Okay, and so on. So this one again. Where is 7 pi over 12? 7 pi over 12. Okay, so that seems like 7 pi over 12. If I added 5 pi over 12, then I would be at 12 pi over 12, which would be pi. Okay, so 7 pi over 12 is not quite 1 pi. Here's pi. Okay, 7 pi over 12 is not quite 1 pi. It's somewhere here. Now, is it bigger than pi over 2. So 6 pi over 12 would be pi over 2, right? So this would be 6 pi over 12, because that's just pi over 2. Okay, so I am slightly bigger than pi over 2, or 6 pi over 12. So 7 pi over 12 is here somewhere. So the question is, and we've already answered it actually, how far am I away then, x-axis to the terminal side of the angle, how far am I away? Well, I'm 5 pi over 12 away, because 5 pi over 12 plus 7 pi over 12 would give me my pi. So from this angle, I need to go this far to get to pi. Okay, so my theta prime in this case would be 5 pi over 12. Okay, and then degrees, let's go back to degrees and do this one. Here we are. Now this one may be a little bit easier. You know, negative 360 degrees is here. You know, negative 270 degrees is here. So you're going this way, and you're saying I'm slightly past negative 270 degrees. Okay, so here's my angle, negative 295 degrees. And then the question is, what's the reference angle from the x-axis there? How far do I have to go? And the answer is, what do I have to add to 295 to get to 360? Or how much do I have to subtract from 295 to get to negative 360? And that would be, what, 65 degrees? Okay. Now notice the reference angles, we're all writing positive reference angles, okay? So that we can do, we can visualize the triangles we've used for the reference angles, okay? And you'll see that a little bit later. Maybe we're going to do that in a few seconds here in our next example, okay? So you'll notice that all the reference angles, I wrote positive angles. So please always use positive angles for your reference angles, because we're going to use those to correspond to our special triangles that we've memorized. All right, so now we're ready to actually evaluate. Trigonometric functions for angles outside of the first quadrant. Okay, so we've kind of been working our way up to this. Quadrantal angles are, you know, most of them are outside of the first quadrant. Okay, fine. But how about the other angles? How about angles like these? Can I find the sine, cosine, tangent, and all the other trigonometric functions of those angles? Okay, and the answer is, of course, yes. Please remember that we call the quadrants are numbered. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. They're numbered. And the answer is yes, I can easily find any of those trigonometric functions for those specific angles, but we're going to use reference angles to help us. Okay, now the way I'm going to show you this, memorizing this is not too important, but it will make you faster as you use these more. So when you get to pre-calc, this is going to become very important for you, and when you get to calculus, you won't even need this anymore, because you would have just memorized a whole bunch of things, trigonometric functions, because you use them a lot. Okay, but what this is saying is, using our understanding that we got here, okay, if you look at this carefully and you evaluate all of the trigonometric functions, it turns out that all of the trigonometric functions are positive in the first quadrant. So we have a way of memorizing this. We say all of the trigonometric functions are positive in the first quadrant. And then if you did a lot of experimentation, you would see that only sine and cosecant are positive in the second quadrant. So we say sine and cosecant, okay, are positive in the second quadrant. And then if you did a lot of evaluation, you'd see only tangent and cotangent are positive in quadrant 3, and only cosine and secant are positive in quadrant 4. So how can I quickly remember which trigonometric function is positive in which quadrant? This is the answer right here, okay? This is the answer. And there's many ways you can memorize this. I think one of them is all students take calculus, something like that. Um, there's a whole bunch of different acronyms and things you can remember. So this will help you probably more in pre-calculus class, but you know, to make you faster, it's always good to know if I evaluate a trigonometric function, where is it positive? So if my angle is in which quadrant, I know quickly if the ratio should be positive or negative. Okay, if my um, trigonometric function should have a negative or positive answer. Okay, so the way I'm going to show you to do this, that's not too important, but it is a good check. It's very good to know this information, but it's not crucial for the technique I'm going to show you to use reference angles. Okay, so let's use reference angles. So what I would do if I were you was this. I would say, let's evaluate tangent of negative 240. Okay, negative 240. So what you do is you say, all right, where is negative 240 in space? So this is negative 90, negative 180. This is negative 270. So negative 240 is not quite there. Okay, and here's negative 180. So there's my terminal side of my angle. The question is, how does this help me at all? I don't know anything else. I'm saying that this is my angle, this whole angle here, this whole angle here is in blue, negative 240 degrees. So let me go in red and draw the reference angle. Okay, what is the reference angle then? So if I'm at negative 180, how far do I have to go to get to negative 240? And the answer is 60 degrees. Okay, negative 180 minus 60 degrees gets me to negative 240 degrees. So here's my reference angle, 60 degrees. So, okay, who cares? What can that do for me? No, very, very important. Remember, for 60 degrees, we have a triangle. Okay, we have a triangle. If this angle is 60 degrees, let me go in here and clean this up a little bit. Okay, if this angle is 60 degrees, my reference angle, all right, then I know that if I drop an altitude and draw a right triangle, this angle here would be 30 degrees. And now we weren't given a length of a radius or something, but I have a triangle that describes all similar triangles for all different lengths of radii in this scenario. So all I can say is, oh, I have a triangle for this, a special triangle. Opposite 60 is root 3, opposite 30 is 1, and the hypotenuse, or in this case, if you want to think about it as a radius, would be 2. Okay, would be 2. And so now I can actually evaluate this, because for any distance here, there would be a corresponding relationship that corresponds to this triangle. Okay, so I can just say, the tangent of negative 240 degrees is, and look at this angle or triangle from this perspective. Okay, that's the equivalent of, in this triangle, the tangent of the reference angle. Okay, now be careful, this side here should be negative because we are in the negative x-axis. Okay, so let me take some of this stuff out of here. So this should be negative 1 because we are in the negative x-axis. Here's the positive x-axis, so negative and positive. So I'm in the negative x-axis, so this side we're going to label as negative, not because the distance is negative, but because we're in the negative direction of the x-axis. Okay, and so basically what you're doing here is tangent of negative 240 is, look at the triangle from this perspective and take the tangent. Okay, so tangent is opposite over adjacent. So tangent is opposite, which would be root 3, over adjacent, which would be -1. So negative root 3 would be the tangent of -240. Okay, um, and you can always confirm this by just punching it in your calculator, if depending on what mode your calculator is in. Now, that's not wise because you'll see that we keep switching between degrees and radians and stuff, and so you'd be switching back and forth in modes and stuff like that. So don't rely on your calculator to do this, but you could check yourself if you really are uncertain about one of your answers. Okay? All right. So let me do maybe one more, and then I'll let you look at the rest. Okay? Maybe do one more here. So let's talk about this one. Let's draw the angle and then find the reference angle. So, and I think if the more you do this, the quicker you'll become at this and go, oh, I'm getting this very quickly now. Okay? So think about 17 pi over 6. I can already see what the reference angle should be. You're thinking 17 pi over 6. If I just add 1 pi over 6, I'd be at 18 pi over 6, which would be 3 pi. So all I need to know is where would I be at that point. So this is 0 pi, 2 pi, 3 pi. Okay? So, all right, this would be pi, and this would also be 3 pi if I go around again. Okay? And so you go, oh, so I'm not quite at 3 pi. I am just 1 pi over 6 shy of 3 pi. Okay? So my angle looks like this. All right? And it's there. Okay? Something like that. Not exactly. This is not perfect. And this would be my 17 pi over 6. But it is just pi over 6 shy of being 3 pi. Okay? And then you ask yourself, what's pi over 6? Well, pi over 6 you should know, that's 30 degrees. Okay? That's 30 degrees. All right? And so now I can think about my triangle again. I have a triangle that's 30, 60, 90. You can think about it as dropping an altitude in there and forming a triangle. Opposite 30 is 1, opposite 60 is root 3. And this would be negative because I'm in a negative x-axis. This is positive y-axis, that's fine. And this would be 2. Okay? And notice the hypotenuse always positive because the hypotenuse corresponds to a radius of a circle, kind of, in this case. Okay, and so now what I would do is say cosecant. So cosecant of 17 pi over 6 is, well, cosecant, I wrote that incorrectly, not cosine. Cosecant, so sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. So hypotenuse over opposite in this case, if I'm looking from this direction, hypotenuse is 2, opposite is 1. Okay, so 2 over 1, so that would just be 2. All right, and then please go do these other two. You can figure them out, and if you need some help, you can check the completed note sheet there. Okay, all right, so let's do this. These last two examples pretty quickly and get it over with. All right, we're almost out of here, guys. So we do this. This says Frogbot, and actually you can go look this up. It's quite interesting. It's a real thing. Frogbot is a robot designed for exploring rough terrain on other planets. It can jump at a 45-degree angle and with an initial speed of 16 feet per second. On Earth, the horizontal distance d, traveled by a projectile launched at an angle theta with initial speed v, is given by this. Okay, a lot of information. They're giving you all this information. Okay. Then they say, how far can the Frogbot jump on Earth? All right. So d is the horizontal distance. So that's what they're asking. How far can it jump on Earth? All right. And this says the projectile is launched, if the projectile is launched at angle theta with an initial speed of v. Okay. So it can jump at a 45-degree angle with an initial speed of 60 feet per second. Okay, So for me, the 45 degrees would be my theta, and the 16 feet per second would be my initial speed, which they said is letter V. Okay, so all you have to do is just plug that information in. What's the distance it can jump? This is asking for what's D. You say V squared, so V here is 16 squared over 32 times the sine of 2 times theta, and theta here is 45 degrees. Okay, so D is, I think if you do that, you get 8 times the sine of 90, and so D is, now I have to show you this. You can enter this in your calculator. Just make sure your mode is correct. I'm in radian mode, so I'm going to switch back to the degree mode. You can do this in your calculator. To check your answer, you just do 8 sine 90. Okay, and you should get 8. Now, that's okay. You know this is 8, but you don't need your calculator because you should know for sine of 90, remember we have this thing, and we said at 90, my unit circle's coordinates are 0 and 1. And so sine of 90 is just the y-coordinate. Sine is just the y-coordinate for quadrantal angles. So that's why you get sine of 1 over 1, which is just 8 in the end. Okay? You shouldn't have to rely on your calculator for that. You can do this by using your quadrantal angles. If you want to, you get lost, please by all means use your calculator. Okay. Rock climbing, let's see this one. Okay, a rock climber is using a climbing treadmill that is 10.5 feet long. All right, so please, what they're saying is this distance here is 10.5 feet. Okay, the climber begins by lying horizontally on the treadmill, which is then rotated. So in other words, the treadmill is like this, the climber is over here holding on, okay, and then the treadmill is rotated like that. That's what they're saying. Okay, and until it gets to this position. All right, and it's rotated about the midpoint. So this is the middle. Okay, this is the middle, and then they're telling you that this distance then is half, which is 5.25. Half of 10.5, which is 5.25. Okay, all right. So that the rock climber is climbing towards the top. If the midpoint of the treadmill is 6 feet above the ground, how high above the ground is the top of the treadmill? Okay. So, if the midpoint is 6 feet above the ground, how high is the whole treadmill above the ground? At the top of the treadmill above the ground. So basically what they're asking you to find is this sliver of distance here, because I know that this is 6 feet, so I'm trying to find this. Okay, and now let's think about this carefully. Let me mark this up a little bit better here. This is my 5.25 feet. Okay, so what we can do is use the concept of a reference angle. Okay, so there's my angle, 110, and actually I don't have to use the concept of a reference angle. We can, but what I can do is drop an altitude in here, and this is the distance we want to find. Okay, I want to find that distance. All right, so if I'm approaching this problem from here, now notice if I use the concept of a reference angle here, I can draw this angle here and say what's the reference angle. But the reference angle here is not something that I've memorized. It's not going to help me be faster or better at finding the answer than just using 110. What's the reference angle? How far do I have to go to get from 110 to 180? It's 70 degrees. Well, I can't use a nice triangle that I know. There's no triangle that has 70 degrees in it. Okay, so we'll end up just using our calculator to evaluate this answer. All right. So in this case, the reference angle is not going to help me much. All right. So all I'm saying is I know this distance right here. I know this distance, and I want to know this distance. Okay? So what you're going to do is say, what you're going to do is this. You're going to say, which trigonometric ratio involves the opposite and the hypotenuse? Because from this angle, if I'm looking at from here, this is opposite and this is hypotenuse. Okay? And so you're going to ask yourself which trigonometric ratio involves hypotenuse and opposite. And so I'm going to say that must be sine. Okay, the sine of the angle 110 is equals to the unknown distance, which I'm looking for, which we can call that x if you want. Actually, let's stick with y, since sine corresponds to y. And then over the hypotenuse, which they told us is 5.25. Okay? All right, so I set something up, and now I'm just solving it to find y. So y is, multiply both sides by 5.25. You get 5.25 sine of 110. Okay, and then y is, again, I don't have a reference angle that helps me here. I don't know what the sine of 110 is, so this is where you rely on your calculator. So you would go here and just say 5.25 times the sine of 110. Okay, the sine of 110. Make sure you're in degree mode. I just switched my calculator to degree mode, so I know I'm okay. So you get 4.93. Let's say 4.93. Okay, and this would be feet. All right. So what we just did is we used trigonometric function to tell me that this distance here is 4.93. Is that what it was? Yeah, feet. Okay, so the question was, how high is the top of the treadmill? The question is, what's this whole distance? So it's the 6 feet plus the 4.93 feet. Okay, so the top is 6 feet plus 4.93 feet above the ground. Okay, which would be 10.93 feet above the ground. All right, hope this helped you guys. Hang in there, persevere. You can do it.